We're a government research organization, and we should be taking the biggest risks. We should be trying things that companies would never try, the really crazy stuff. Because maybe if we have a success there, that'll create a whole new string of companies that would dramatically increase the amount of energy we could produce and reduce costs substantially. So we should be taking the big risks. And that's what we started JBEI doing, with the biggest risks.
By setting up that high risk, high payoff entrepreneurial spirit, we were able to infuse the researchers and the postdocs and the scientists here with a sense of excitement and being on the cutting edge of things, as opposed to a more status quo, business as usual research environment.
And so that kind of integrated approach and a large-scale effort like this, where we're trying to do basic science, but we also have a sort of societal mission, is really unique.
It helps that we're working on probably the biggest challenge that humankind is facing right now, and that is producing energy that is friendly to the environment. One thing that's, I think, unique about this place is it's very entrepreneurial. And I think we try to breed that in people and try to bring it out in people. And we attract people who are like-minded. And we want to give them the vehicle for expressing that.
The JBEI value proposition is that we took a look at the problem set and the challenges and the gaps and the potential solutions to addressing the needs of replacing liquid transportation fuels and also chemicals that are derived from non-renewable sources such as petroleum.
The point about bioenergy, it's not a single problem, it's a whole raft of problems altogether. So by having me having to talk to engineers repeatedly and explain what I'm doing and talking to people who are doing life cycle analysis, the more you talk, the more you can understand the language you're using and really start to solve the problem. It comes together much more quickly than having, say, a meeting every 6 months or a year. Because if you're talking day to day, you're really making the progress day to day.
It's a big challenge. Making drop-in fuels is tough, but it's a challenge that we have to tackle. I talked about the fact that the fleet turns over fairly slowly. Once you buy a car, even if you don't keep it for more than 10 years, it ends up on a used market and somebody else is driving it. And so it may be on the road for 25, 30 years maybe. And so if that vehicle isn't compatible with the new non-drop-in fuel, that means you still have some demand for traditional gasoline or diesel, as the case may be.
So what we're trying to do is increase the amount of knowledge about the plant cell wall. It's kind of surprising that even though we use it for foods and materials, the clothes you wear, the paper you write on, we've used it for thousands of years. We actually knew very little about the fundamentals of it and the fundamental biology. So we're trying to increase the amount of knowledge that's available. And this does two things. One, we can actually try and make a better plant, but we're actually just trying to make enough knowledge available that a plant breeding company can come along and use that knowledge to make a plant that suits their ends. No one solution is going to fit everybody, because even within the US, there is land that is dry, there is land that has cold and altitude and different diseases. So we have to make the knowledge available that people can then choose the traits they need for their plant of interest. Switchgrass is great because it grows with very little water and fertilizer. So every time you add water and fertilizer, you're really, really increasing the environmental and economic cost of your feedstock. And one of the critical things to producing environmentally and economically viable biofuels is, of course, the cost of feedstock.
Switchgrass is a good biomass crop because it's perennial, meaning that you don't have to plant it every year, and it comes back more quickly in the spring than plants that have to grow from seed.
So we are interested in understanding how plants use the energy from sun to turn it into sugars and build it up into their cell wall, and use that understanding to make plant cell walls that the deconstruction division can more easily break down and turn into fuels with the help of the fuel synthesis division.
We start off with a plant. This is corn stover, which is the non-edible part of the corn plant. We chop it up into small fragments, and then what we do is combine and heat these small fragments of the corn stover with this liquid. Now this liquid is actually a salt that's a liquid at room temperature. And what we do is when it heats it up, we get a mixture that looks like this, where the corn plant is partially degraded. And then what we do is we take and we pour water in here, and from this slurry we get a pre-treated corn stover where the sugars are much more easily removed using enzymes and microbes to a sugar that can be converted through engineered microorganisms that we've developed at JBEI to a drop-in replacement for biofuels. And you can see that this is actually a product made by an organism developed at JBEI, and it floats to the top of a water mixture, which means it's like a hydrocarbon.
The main source of carbon is sugars, and so our organisms love to eat sugar, and we could take the carbon that's trapped in the sugar and we can, through a series of different enzymes, convert that carbon into our fuel molecule, which is also made of carbon, just in a different arrangement. We come up with new fuel molecules, and then we insert them into either bacteria or yeast, which are two model organisms that we use because it's easy to get stuff into bacteria and yeast, and a lot is known about their genomes. And then ideally, we will be able to produce the fuel in a high enough titer, titer just meaning a lot of it, in order to send it off to another place that has larger fermenters in a larger scale, where we could produce the fuel at large enough quantities where we can actually use it in different things like cars, planes, lawnmowers, whatever. We have ABPDU, which is downstairs. What they do is they'll take our most useful strains that look the most promising, and they'll test them under various bunch of conditions that will probably be applicable to larger industrial scale settings.
For all of these technologies, our goal is to help bring them close to commercialization, but not necessarily all the way there. So what we try and do is replicate all of the conditions that you would see in a commercial operation so that somebody could essentially take technology from this facility and go directly to a commercial scale application.
And if they look promising, they can go on from there to even larger scale-ups and potentially be licensed by different industrial companies.
Bioeconomy has the potential to provide socioeconomic benefits, environmental benefits, and hopefully provide us with a more stable supply of energy.
What we're doing is important for the future of the planet, because if we get this right, we'll reduce the amount of greenhouse gases put into the atmosphere, maybe even pull some of that carbon out of the atmosphere and be able to save the planet.
We stand at an inflection point in this modern era, that whether we're going to stay with the status quo and stay with fuels and chemicals that are derived from non-renewable resources, if we continue to maintain our ambition to not create a sustainable future for the generations that follow, or do we make a decision? Do we make a conscious decision and commit our will towards making a future that is better than the one that we live in today?
We use the technologies that JBEI has developed for many other things besides fuels. Fuels is only one thing. If you think about a barrel of petroleum, 15 to 20% of that barrel goes into producing all the chemicals that we encounter all the time. So the carpet on the floor, the paint on the walls, the ceiling tiles, all of those things, toothbrushes, eyeglasses, all of those things come from petroleum. And there's no reason why we can't engineer biology to produce those same things, drop-ins, that would replace those chemicals we would ordinarily get from petroleum. And what that does for us is that it, just like chemicals are higher value than fuels, and in some sense the chemicals industry enables the fuel industry, or they play off each other. The same thing will be the case for chemicals produced using biology and fuels produced using biology, is that those chemicals will help enable that.